Okay, so as we draw towards the end of day two, very time team thing to say, it gives me great pleasure to introduce Peter Enrico for his second session here. Take it away, Peter.
Hey, thank you,
one more
Martin.
thing. Sorry, one more thing. Yeah, the usual thing I always forget to say, which is please do use the QR code for evaluation.
Yeah,
Sorry.
thank you, Martin. Yeah, my QR code's right here if anybody wants to take a little snapshot of it now. But let me change the pointer options here. All right, let's get started. Good morning, good afternoon, good evening, everybody. As we just said before, my name is Peter Enrico of Enterprise Performance Strategies. And today what we're going to talk about are the SMF 99 and 98 records, which we call the high frequency measurements. So this is sort of an introductory type of presentation to kind of give you an inventory of what is in these records, some sample reports, some kind of things you might want to think about and why you might want to cut them, and what they're meant to highlight and measure and give us insights into. So let's go onward. Just a few administration things first. Always remember that our mission at Enterprise Performance Strategies is ZOS performance. So whether it be, you're monitoring the system, measuring the system, analyzing the system, doing a health check, whatever, think about us. We do have our product called Pivotor, which does SMF data reporting, and all the reports in this presentation are from our Pivotor product. In addition, we do some educational workshops, performance educational workshops. We have 3 of them coming up. They're listed here. We have our Essentials ZOS performance, which is, processor storage, some IO, pricing, and several other topics, some workload manager. And that's taught by my colleague, Scott Chapman, who gave a presentation earlier today on DDF and DBATs and whatnot. We also have a 2-day parallel SysPlus class, which will go through coupling facility structures and whatnot. And then we have everything workload manager as the final class, which is a 4.5-day class. All the classes are given remotely, so it's a session just like this. And one of the interesting things about the classes is before the class, we ask you to send us a set of SMF data. And then in the class, not only are you learning the subject matter, but you're going to be doing an actual analysis of your own environment. So consider that. They're great classes. And also consider that we do consulting assignments for performance as well. One other thing I just want to mention is that my colleague Scott Chapman and I, on a regular basis, basically every 2 weeks, we give a series of free half-hour performance webinars. So it's pure education. And typically the presentation is about half an hour, maybe sometimes a little bit short, a little bit long, but just basically about a half an hour. Again, pure education about a various subjects. And then Scott and I will do a Q&A for the next half hour. So go to our website, sign up for the webinars, at least get notified about them. You can sign up for them. If you attend, you attend. If you don't, you don't. But here's a list of the webinars that we're doing for this season. The ones with the check marks are already completed. And you can get a copy of the presentations at our website, which is listed in the presentation. So these are the remaining ones, and then we'll take a short break, and then we do another every 2 weeks. So certainly consider that. And also remember that if you ever want a free cursory performance review of your environment, Scott and I love doing these. You send us a little bit of SMF data, and then we'll have a phone call with you. It's usually about 90 minutes. And it's a good way for us to introduce ourselves to you, for us to get to know you better. And then finally, you get to see our product, and we absolutely do a performance analysis, so you will get something out of it. And again, if you're ever interested in that, just go to our website, and you'll see that it has cursory review. Also know that we do have a free tier for our Pivotor product as well. All right, so let's talk about high-frequency measurements, the SMF 99 and the SMF 98 records. So the purpose of these high-frequency measurement records is to help us understand what we call transient performance problems. And what a transient performance problem is, or performance, not to be a problem, it could just be, just transient performance. It could be, it's something that typically lasts for a short period of time. So in other words, many times we have our 15-minute SMF measurement, but a lot can happen in that 15 minutes. And what the transient measurements are, these high frequency measurements are, is helping us break down that measurement interval into much tinier chunks so we can kind of see what's going on moment by moment. So for example, today we have what we call the SMF 98 and 99 records. And the recommendation here is to make sure you start recording these records. And I'm going to go through them in a little bit more detail. There's not as much detailed data in these records as you're going to find in the standard SMF records, let's say for the RMF or CMF. But what's nice about them is the measurements that they do include are quite useful in understanding these short-term problems and performance phenomenons. Many sites do cut the 99 records. Not as many are cutting the 98s. We recommend both of them be turned on. And again, I'm going to give you some options in a moment, but that's kind of the overall recommendation, is to get these records turned on and use them. So at a very high level, the first record we're going to talk about in a few slides is the SMF 98 records, which is the HFTS records, which is your high frequency throughput statistics. In the SMF PRM, if you have this parameter specified, that's how you basically get it turned on. We recommend that you have this set for a 5-second interval, but you can use the intervals that we have listed here. And a 5-second interval will give anywhere between 400 and 500 megabytes per system per day. That seems like a lot, but when you compare it to your CICS or DB2 data, it really isn't very much at all. The next record we're going to talk about in this presentation is the SMF 99 record. And our recommendation is, at a minimum, turn on the subtype 6, 10, 11, 12s, and 14s. Again, I'm going to go into this in much more detail in later slides as we talk about the 99 records, but this is sort of an overall recommendation. The SMF subtypes, 99 subtypes 1, 2, and 3 are also quite useful if you decide you want to turn those on. And in fact, later in this presentation, I'm going to give you some examples of using the SMF 99 subtype 1s and 2s. Yeah, that's what we say. The main thing I would recommend also, as it says here, is the SMF 99 subtype 13. At the very least, make sure that if you do have the 99s turned on, make sure you specifically disable the SMF 99 subtype 13s. I'm not even sure why they're there. Obviously, they're 99 records, but they are at IBM internal use only. The mappings are not available, and they're very, very high volume records. And so because they're so high volume, we don't know how to look at them. I don't know of anybody who even looks at them other than IBM during debug. I would say keep those turned off. Don't waste your SMF processing on the 99 subtype 13s. One big caution I always give about these records is be careful of getting wrapped up in reporting of these measurements real time. I'm always kind of amazed that you have some customers who are maybe using something like Splunk or one of the other type of products like that and trying to get these things reported every 2 seconds. All right, so you're looking at CPU utilization every 2 seconds. Looking at it real time, I'm not quite sure what you can do with that. I've never really found a good use of these records real time. They're more for post-analysis and debug and getting insights into your system. But if you want to look at them real time, fine. I just don't know if it's really worth the effort. So let me give you a classic example of a transient performance problem. It doesn't have to be a problem. I shouldn't say the word problem, but it's really about a transient performance issue, some sort of phenomenon in terms of utilization or usage and counts and things like that. What we're looking at on this chart is a KEC utilization, CPU utilization chart. So the scaling of the chart is from 0 to 100%. And what we have here is all the LPARs listed that are on this KEC, on this machine. And we're looking at CPU. And what we're looking at here is a typical RMF, CMF interval SMF measurement to see how busy the machine is over a period of time. And this looks like it's from 9 o'clock in the morning until 12 o'clock in the afternoon. And you can see that utilization is broken down by LPAR. So one can conclude, for example, that, oh, look at this interval I'm pointing to here at about 10:15. The machine was about 58% busy. I have lots of white space. And you do, on average, over 15 minutes, you have lots of white space. But what the SMF 99 and 98 records help us do is to gain more granular insight into the utilization. So here's an example of the same exact period of time, right? The same exact window we looked at in the previous slide. But instead of looking at 15-minute measurements, these measurements are the CPU utilization of the KEC every 2 seconds. So now what we're looking at is, instead of a 15-minute average, we're looking at utilization every 2 seconds by these blue dots. And you can see that there are periods of time that were much higher, even though we know that we had a lot of white space. In fact, if I superimpose the two charts over each other, which is a feature that we do with Pivotor all the time, what we're looking at on this particular chart is the average utilization every 15 minutes of the KEC along with each LPAR. And then here, broken down by LPAR. And then here what we have is the utilization every 2 seconds. And so here, take this interval here that I was pointing to before, where we said, oh, look, it's about 57, 58% busy on average over 15 minutes. But notice that there's a lot of intervals where this guy was much, much more busy. In fact, there was a period of time when he actually was at 100% busy. So this is a case where a customer calls up and they say, oh my gosh, my workload's delayed. I had everything froze for like, a minute, everything froze for like 30 seconds or whatever. And you look at the average utilization, you say, well, it's 57%. It's not due to CPU. But now we know that when we look at the utilization every 2 seconds, that it could actually be due to CPU. And then what we're going to see in the 98, 99 records is we can kind of gain insights as to what happens at this granular level as well, not just utilization. So that's sort of an overview of why we may want to use these measurements. So what I'm going to do is I'm going to give you an overview of the SMF 98 records, and then I'm going to do the same thing with the 99 records. So the 98 records are a few years old now. I should remember when they were introduced, but let's say it was 5 or 6 years ago. I don't even remember, but they've been around for a little bit of while now. Most customers we find don't have them turned on, and that's okay, but we do recommend you turn them on. There are some very interesting statistics in them, and if you can deal with the SMF volume, which is not terrible, but if you deal with the SMF volume, they are very useful for performance analysis and debug. So relatively new SMF record, and what we see here is that the metrics include some utilization values, concurrency values, efficiency values, and contention and queuing. So I'll show you what that means. But basically, there's going to be measurements about locking. There's going to be measurements about the dispatch queue. There's going to be utilizations and all sorts of things like that. The way you enable these records is through the SMF PRM member or Palm Live, and you have to make sure you enable the 98 records. But also what we're going to see is that you have to specify this high frequency throughput statistics interval parameter to tell how many seconds you want each interval to be. Again, we usually recommend 5-second intervals. If you specify no HFTS interval parameter, it disables the recording of the 98 records. So specifying the 98 records as a type is not enough. You have to actually turn on the HFTS parameter as well. And again, these could be somewhat voluminous, but again, when you compare them to your 110s or your 101s, they're probably not that voluminous. Some examples of measurements that we're going to see in these, and there's quite a lot of measurements, but some of the things we're going to see is you do have measurements that give us processor configuration information, so we can kind of see what the setup is, and some hyperdispatch pooling measurements, which I'll show you examples of. And again, hyperdispatch pooling measurements are in the SMF type 70 record, so you do get them on a 15-minute basis. But here we're talking about the pooling every 2 seconds. So you get it on a much more granular basis, parking and unparking. And I'm going to show you an example. Utilizations broken down by hyperdispatch pools, insights into latent demand. So as you know, your processor is going to be busy and work can back up. What does that backup of work look like? What does that dispatch queue work look like? And then we're going to see in a moment that that dispatch queue breakdown is going to be broken down by buckets of high dispatching priority work versus medium and low dispatching priority work. And I guess that's what I'm saying here as well in the next one. And there's going to be some spin and suspend lock processing insights. So what's nice about that is that if you do have sort of a freeze or something's happening, but it doesn't seem to be global, it could certainly be due to locking. And so it's always nice to get that locking information as well. I'll be honest with you that we use the records. We've actually been quite successful with them, but I don't see them as the panacea record for performance debug. They are quite interesting. There is some good information in them. Some of the data is for giggles and kicks, as we say, to give us some additional insight. But it's more for really a debug type of purpose. So for example, here we're looking at how busy the CPU is, and the measurement for this particular system, this is on an MVS basis, is we have the core CPU busy and the CPU busy itself. Why there's slight differences in the two, I have zero idea, but at least it gives us some insights into how busy this KEC is. And again, we're looking at it on a 2-second basis. Here's an example of the hyperdispatch pooling, which if you want to see how the, the utilization by pool, well, this is what this is going to give us. So what's happening here in this particular slide is we have 3 series for your high pool processors, your medium pool processors, and your low pool processors. And now what we're getting insights into is how busy each one of those pools are. Interesting measurement. Don't forget that, you know, the low pool processors are not going to be favored, and they could be shared with other LPARs. The high pool processors, you may have more of them. So looking at the utilization of each pool is interesting. They're not necessarily normalized to see how busy each utilization is relative to how big the pool is, for example, or something like that. Another thing that we get in this record is some mean time to wait measurements of the core. So as a reminder, what mean time to wait means is basically how much time typically goes by before the workload, before the system goes into a wait state. And what a wait state basically means is that the system is saying, I have no more work to do. So a good example of a low mean time to wait workload would be sort of a CPU. I'm just going to make sure I don't get it backwards. A low mean time to wait means you're only waiting a short period of time. Could be something like an IO intensive workload where you do a little bit of work and then you're off for a long period of time doing an IO, versus a high mean time to wait, which means you're constantly pounding against the CPU and you're never really going into a wait state. You want to use the CPU. So this is kind of helping us to understand the average mean time to wait, that we see the higher the numbers is typically due to more of an interactive workload or a CPU intensive workload, as opposed to a low mean time to wait, which tends to be a IO intensive workload. Again, kind of interesting. I'm not sure exactly how to use this, but again, think about it as I have a performance problem. Let me see if any of these measurements don't follow the typical pattern, that kind of thing. Here's an interesting one where in the SMF records, we also get work unit queuing and priority queuing by buckets. So basically what's happening here is you have your processors and the processors are busy. So there's always a possibility of work queuing up to wait to use these processors. So what we're always interested in is how long is this queue of work waiting? You know, is this a short queue? Is this a long queue? And there's some insights into that when we look at the SMF type 70 data. But now what we're looking at is the same sort of measurement, but on a 2-second basis. So in this particular case, or 5-second basis. So in this particular case, what we're looking at is the queue depth, but in this particular case, it's also the queue depth by bucket. So but what happens is that the work is going to be assigned a CPU dispatching priority. So high CPU dispatching priorities at the front of the queue, low CPU dispatching priorities at the back of the queue, and then there's the middle of the queue, of course. And so what's happening here is the measurements divide these dispatching priorities up into high, medium, low type buckets and discretionary. So what we can get to see here is, all right, not only do we know the queue depth, but what is the basic relative CPU dispatching priority of the work that's backing up? Is it discretionary work that's backing up? Is it high priority work that's backing up? And that's an important insight to understand when you're trying to understand the load being placed onto your system, understanding latent demand and what might be delaying your high importance workloads. You know, it could be that you're a high utilization and the latent demand is building up, but if most of the work building up is low dispatching priority work that you don't care too much about, you might not care. It's the high priority work you're probably more interested in if that work is backing up. So this gives us some insights into that kind of measurement. I guess this is something similar. I'm not sure why I have both of these, but it's basically a similar measurement here. Yeah. And there's lots of other measurements. What I didn't give you here is the locking measurements. Just helps you understand what kind of locking is going on. So what's nice about the 98 records, again, if you want to dabble on them, is they do contain some low-level diagnostic information to do performance analysis, performance debug. You know, whether you have a transient performance problem that comes in, you want to see what's happening moment by moment, and that's what these are used for. Most of the data in my mind is meaningless. I mean, if I was going to look at this measurement every 2 seconds to see the queues build up, yeah, that's interesting. It's going to make a nice graphic on your real-time monitor. I don't know. It's kind of interesting, but you're not going to be analyzing it real time. You're really going to be looking at it on a post-analysis when you have a performance issue you want to analyze. So just remember, when you look at these measurements, you have to understand what normal is, because looking at queue depth is not enough. You have to understand what your queue depth is relative to what your system is in your technology and whatnot. So understand that these measurements can vary greatly by environment. They can vary greatly by times of day, by workloads, by operating system, by machine configurations. So always make sure you look at these measurements in context of the environment you're running in. But again, they're great for performance analysis and performance debug. I will say this, that the 98 records, in my opinion, are not fully understood. I think we use them more than most people, and we understand them okay. I wouldn't say we're experts at the 98 record, and I've not met anybody, not even the IBM is experts at the 98 records. So it's interesting. We're going to see how this record evolves in terms of usage. I expect it to grow over time with more additional useful measurements. But again, for debug, it's great. Yeah, so that's what I wanted to say here. So that's the 98 records. There's really not much to say. Again, there's not like you're going to have this regular reporting. The 99 records, on the other hand, I think are extremely useful and should be looked at on a regular basis, not just during performance debug or during a special analysis. So let's talk about the 99 records a bit. Now, there's lots of subtypes of the 99s. So let me go through them, and I'm going to give you some examples later on of some of these subtypes. But let me just kind of give you an idea of what's happening here. The first subtype of interest is going to be the SMF subtype 1. And what the SMF subtype 1 is going to be a system level measurement data. So basically, for those of you who don't know, the way Workload Manager works is it wakes up every 10 seconds and does some bit of analysis. And then based on that analysis, it can change a control like a dispatching priority, all with the objective of meeting goals. Right, so that's what's happening every 10 seconds. Every 2 seconds, this also doing something, but every 10 seconds is the main loop that we think about. So naturally, if WLM is waking up every 10 seconds, it has to monitor what's going on in the entire environment, as well as on a per WLM service class period basis. So to monitor what's happening in the entire environment, that's what the subtype 1 is all about. When you look at the subtype 1, you're basically looking at SMF measurements that are basically system monitor measurements. How busy is the system? What's actually happening on the system? What's the storage usage? What's the dispatching? What's the workload going on? The IOs and things like that. What's the consumption of the system? And again, this is at a system level. And then this is also where we have WLM trace actions, which I'm going to give you examples of towards the end of this presentation, so we can understand WLM's decision-making process. So think of subtype 1 as being a system level record that helps us monitor the system. Subtype 2, on the other hand, is a service class period measurement data. So what's happening here now is it's breaking down the system measurements by workload. So this is where we're going to find out on a service class period basis how the goal is being met, that using and delay samples, what's the storage usage, all sorts of things, but on a period by period basis. Everything WLM needs to know about that period in order to make an adjustment. So if you want to understand maybe the CPU usage of a particular service class every 10 seconds, that's what you would do with this particular record type. And I'll show you examples of the subtype 2. Subtype 3 is more of an obscure record or obscure subtype. This is what we call plot data. Later in this presentation, I give an example of a plot. But what happens is for Workload Manager, for it to make a decision, it's using the subtype 1 and subtype 2 type of data, the measurement data on a system basis, the measurement data on a period basis. But in order to make a change, WLM has to project what's going to happen in the future if it makes that change. If I raise the dispatching priority and get rid of so many CPU delay samples, what's that going to do to my goal and utilizations and things like that? And to do that, WLM needs to do projections. And to make projections, WLM has what we call plots. And the plots, if you put them on a graph paper, you actually see a plot, and then you can make a projection based on what the graph is telling you. That's what the subtype 3 is all about. Subtype 4 is less interesting these days. And this is going to give us this device cluster information for our logical volumes. Before the advent of parallel access volumes, what WLM did was controls the IO dispatching priority. So you have what's called the CPU dispatching priority, which gives us prioritization onto the CPU. And you have an IO priority, which gives us prioritization as to who can do IO to a specific logical volume. And that's the IO priority. So before the advent of parallel access volumes, WLM would control that CPU dispatching priority for a particular workload for a logical volume. And to do that, what WLM would do is gather information about device clusters, meaning what groups of logical volumes are being used by which service class periods. I might have a service class period called DB2 high, and you might have a set of logical volumes that are called DB2 whatever, and those are the logical volumes DB2 high is using, where batch low is probably using a different set of logical volumes. And the reason WLM needs to know that information is to be able to control the dispatching priority. In today's day and age, you're probably using parallel access volumes. Our recommendation, our general recommendation, is to turn off prior IO priority management, and we've given webinars about that. So certainly I would recommend turning off IO priority management, and instead what you want to do is use parallel access volumes. The result is that the SMF 99 subtype 4 is not going to be that interesting. Subtype 5 is about monitored address spaces. All this means is that sometimes WLM, what it'll do is select an individual address space to pay attention to. In other words, we think of workload manager as managing these service class periods, and it does. But sometimes to make a service class period meet its goal, I don't need to help all the address spaces. I might need to help only one address space, one big DB2 or one big CICS or what big batch job. So sometimes what workload manager will do is monitor individual address spaces that it finds interesting. This record is about those address spaces. Subtype 6 is the best record that I would say at a minimum, always cut the subtype 6. And this is going to give us our service class period settings every 10 seconds. So this is what's going to tell us what the performance index is, the CPU dispatch and priority, the CPU consumption, storage controls every 10 seconds, so we can see how WLM is managing a particular service class period. Subtype 7 is some about the parallel access volumes. Subtype 8 is about LPAR CPU management if you're using IRD. Subtype 9 is channel path measurements. And subtype 10 is a record of this. If you made a dynamic speed change on the processor, it records that speed change. Subtype 11 is if you're looking at group capacities and how the group capacity is being used. Subtype 12 is a very interesting record. That's hyperdispatch, and you want to see the hyperdispatch pooling and parking and unparking every 10 seconds. And then we have the 13, which I said was internal use. So I would say turn that off. And then we have some hyperdispatch topology information inside of the subtype 14, which is just basically a mapping of the processors to the actual physical CPUs on the CEC. So you can kind of get a diagram of how the CPU is set up. That's my high level overview of the records. I'm going to go into some examples now, but kind of recommendations I would say is consider regularly collecting the SMF 99 subtype 6, 11, 12s, and 14s. In fact, we tell all of our customers to, at a minimum, always send us those records for reporting because they are invaluable. And again, I'm going to show you some presentation examples. Collectively, there are about 40 megabytes per system per day, which isn't really very much, so I wouldn't worry too much about that. Additional records you may want to collect. I always like getting the SMF 99 subtype 1s and 2s at a minimum because I always like looking at, what's happening on a system basis, what's happening on a period basis every 10 seconds. And these are quite useful when you're doing sort of a debug of, when I do a lot of WLM analysis, so you can imagine I find it very useful to help me debug things or help a customer understand what's going on in their environments. Subtype 3, I like cutting only because I like looking at the plots. If you're ever interested, again, just take the measurements, you put them on a graph paper, and you'll see how WLM does its projections. And then some information about monitored address spaces, only because I like to see what address spaces WLM finds interesting and may be controlling individually, sort of outside the period, not outside the period, but specific as opposed to period-wide. And I would say then call myself or my colleague Scott Chapman, and we'll help you with these records if you want to do a review of them, is what I would always recommend, because they are interesting if you want to see what yours looks like. So let's go through some examples. The first one is SMF 99 subtype 6, which I did say is probably the most valuable SMF 99 record that I would say you cut on at a minimum, cut those records. They're cut every 10 seconds. Oh, I'm sorry. One other thing I want to point out about these records is that some people are nervous about turning on the records because it's going to add additional CPU overhead to all of a sudden start collecting these measurements. That's not going to happen. And the reason that doesn't happen is for the base measurements in the SMF 99 record, meaning the ones through the subtype 1 through about subtype 12 or 13, 12. I don't know about the 13s. is that this information, the 99 record information, is being generated regardless if you have the 99s turned on or off. So in memory, Workload Manager is constantly cutting these records and pushing them out, cutting these records. Your turning on the record just merely takes the record and puts it to the SMF file. So turning on is not going to add additional CPU measurements. It might add additional volume to your SMF, but it's not going to add much or very much at all of additional CPU to cut the measurement. So you have these measurements being collected today. It's just a matter of enabling the record to get them put out to SMF. So don't worry about the overhead of having them turned on. What's in the SMF 99 subtype 6, which makes it so valuable, is service class period and goal information. So we get to see what the goal is every 10 seconds. That's kind of interesting. If you're not changing a lot, it's not going to be interesting at all. Your performance indexes every 10 seconds. So many installations are looking at performance index every 15 minutes. And I can tell you a 15-minute performance index is sort of a squishy feeling you can get for how well the work is performing relative to workload management. But looking at the PIs every 10 seconds is quite insightful. And this also gives us what we call the sysplex PI and the local PI. I'm not going to go into that here, but just understand the local PI is how well WLM thinks the work is running on this specific system, where the sysplex PI is how well WLM believes the work is running on the sysplex as a whole. Both interesting measurements. We also get the CPU and IO dispatching priority values, CPU service consumption. So we get the service consumption every 2 seconds, 10 seconds rather. MPL information, stores isolation information. And this is the one record that we get that gives us insights into what we call the $SRM-S guys, or what we call the internal periods. So the internal periods are ones that are not defined by you, but actually defined by Workload Manager. What many people don't know is that you define a series of service class periods, but there are cases where WLM feels it needs to create its own service class periods for management of certain address spaces. And those service class periods that WLM dynamically creates and actually takes address spaces out of where you've assigned them and put them into some place that WLM wants to put them, those are going to be what we call the $SRM address service class periods. And I'll show you an example. I think I have an example of that. So what's good about these records is over time we can actually, I'm sorry. Oh, made a mistake here. What's nice is over time we can kind of see how the dispatching priorities change, how WLM is managing the workload over time. Relative to the goal value, we get to see how well the goal is being met, but we can look at things at an importance level. How much service is accumulated every 10 seconds, which is nice because typically when we look at service consumption, it's every 15 minutes. Now we're looking at it every 10 seconds. You can see spikes in service. And if you correlate that back to the 98 records, you can actually see that when I had a spike in CPU, what workload it was for that 10-second period of time or whatever it is. I'll show you an example of CPU service consumption by priority, which is quite interesting. And we'll see the relationship between the sysplex and local PI, the server and served relationship, which is those $SRM-S periods, and different types of protections that WLM puts on. So let me show you what I'm talking about here. What we're looking at on this particular slide is the SMF the CPU dispatching priority of the workload every 10 seconds. So it looks like a big old gobbledygook because we're looking at 24 hours worth of data here. And what we see here is each service class period that has been defined, and we can see how the dispatching priorities go up and down. When you look at it like this, it's interesting, but then what we do is we can look at, well, what's just this one period? How's its dispatching priority changing? How's this dispatching priority changing for this period versus another period? So for example, if I zoom in, what we can look at here is I can say, well, I want to understand the dispatching priority of STC high relative to hot batch. And so here, I'm just looking at those two periods, and I can see that generally speaking, a lot of times STC high is above hot batch. There are cases where they're reversed, where hot batch is above STC high or equal to STC high, and we gain those insights. Maybe not the best example in this case, but if you want to see how, for example, What's the CPU dispatching of batch high versus batch medium versus batch low? What's the dispatching priority of DB2 regions relative to CICS regions relative to something else? And that's what's useful to looking at these measurements of the CPU dispatching priority. You get to see who's running above who and how WLM is actually changing those measurements. Well, we also tend to look at, I don't know if this is a good example here, but when you see a big drop in CPU dispatching priority, like I'm pointing to here, and all of a sudden WLM quickly regains that dispatching priority to a higher level, that's the kind of stuff we don't like to see. And that's the kind of stuff that we want more predictability in our WLM management. So what we do is we tighten the goal a little bit to get that less up and down motion of the dispatching priorities, to have a more predictable management or predictable performance by the workloads. Here's an example of looking at the PIs. In this particular case, I'm looking at the performance index of STC high, but I'm looking at both the local performance index and Sysplex performance index. The Sysplex performance index is going to give us insights into how well Workload Manager believes STC high is doing throughout the Sysplex. Almost like as if we took all of our systems, crunched it into one big set of numbers. How well is the work performing across the Sysplex? And we see it's doing pretty good. Where here, we see the local PI is going up and down quite dramatically. And it could be that, yeah, throughout the Sysplex, STC high is doing okay, but on this one system, it's struggling. Why is it struggling? What is on this workload, on this system, that's causing STC high to struggle more during certain periods of time? By the way, I say this is the PI. The values here, the PIs are scaled by a value of 100. So 2 means PI of 2, basically. So you get the idea there. So we get to see what the PI is, local versus Sysplex. In this particular case, I would certainly look to see why the work on this one system is suffering relative to other systems. What is causing this work not to get good PIs? Here's an example of looking at service consumption every 10 seconds. So again, here we're talking about, this is only 1 hour's worth of data. This is for the 9 o'clock period of time, as from the time axis here. And what we're looking at here is what is the CPU service consumption for each of my WLM service class periods every 10 seconds. And we can see here that this one workload called STC low is a big consumer. And down at the bottom here, we have system service class, and this little gray up, this little blue up here appears to be discretionary work. And what's nice about this is that when you look at the CPU utilization every 10 seconds or every 2 seconds, and you see a burst of activity, a high utilization at 100 for, let's say, a minute or two, we can actually come here and look to see what workloads are causing that high utilization, what came in that's causing this burst of CPU usage, and we get to have it on a workload by workload basis now. This is CPU utilization. It's not CPU utilization, it's CPU service units, but we can kind of think of the profile of the chart as being utilization, let's say, every 10 seconds. What we can also do is if I take the CPU dispatching priority values, which we know, and we take the service consumption that we know, what we can actually do is to look at the service consumption by a particular period relative to its CPU dispatching priority. So for example, this is for the 9 o'clock hour, right? The profile of this chart is how busy this environment is in terms of CPU consumption. The blue is how much CPU service is consumed by, in this case, STC high. So we see over the hour, STC high is only using a small amount of CPU relative to the overall usage of the CPU. The gray above the blue is how much service is being consumed by work running at higher CPU dispatching priorities. The gray below the blue is how much CPU is being consumed by work running at lower dispatching priorities. And yellow is how much CPU is being consumed by work running at the same dispatching priority. And what's nice about this is we can look at a graph like this one and see that, all right, the workload's not using that much CPU. It looks like it's relatively high CPU dispatching priority. There's not much work consuming CPU before it. And when this guy is done using the CPU, he's leaving lots of CPU that can be consumed by work running at lower dispatching priorities. Relative to something like this, where we're looking at STC low, we see it using a lot more CPU, right? And we also see that sometimes it gets down to 0 here, which means by the time STC low is done consuming CPU, either it left no CPU over for anybody else, or it could actually have been that it didn't even get all the CPU it wanted. It was, it probably wanted more CPU. It's just that we can't do, we can't see what the latent demand is on this chart. But the point is, we get a feeling for this is a big consumer of CPU. There's work running at higher priority that's kind of getting its work done. As we saw in the previous chart, it was the other one, was that STC high. And in this particular case, we do see that there are times when STC low doesn't have enough CPU and it doesn't leave enough CPU for work running at lower dispatching priorities. Again, all helping us understand when we tune the goals, how to sort of monitor the goals and manage the goals, so that I want to make sure that this workload gets the CPU it wants. Maybe I don't care about STC low, but I care about STC high. I get a good feeling that if I raise the dispatching priority or do something, I can actually change the dynamics of how the CPU is consumed relative to the dispatching priority. Here's an example of, again, looking at CPU dispatching priority, but what I'm actually looking at here is two sets of CPU dispatching priorities. On the left here, we're looking at 1 hour from 11 o'clock to noon of the CPU dispatching priorities of my workloads that I've defined. On the right-hand side here is for the same exact period of time, for the same exact system, the internal periods and what their dispatching priority is. And we can also get the service consumption by these. These internal periods contain address spaces. They wouldn't exist really if they didn't contain address spaces. And typically the address spaces you're going to see here are CICS address spaces, IMS address spaces, WebSphere servant regions, and stored procedure address spaces. So those are the kind of address spaces we see in these dynamic $SRM periods, but we get to see what their dispatching priority is relative to the dispatching priority of the work you've defined. And we could do the same thing for service consumption. So the 99 subtype 6, we always love it. We always ask for it. If you want to send us your 99 subtype 6, I can show you lots of slides and lots of graphs that show you, gives you some insights, and they are quite interesting. Another record of interest is the 99 subtype 12 record, which I had mentioned earlier, which is the hyperdispatch record. And this record is cut every 2 seconds, as opposed to the 99 subtype 6, which is cut every 10 seconds. And the purpose of this record is to help us understand things that influence hyperdispatch decisions, such as pooling and parking and unparking. We do recommend that these records get turned on because they do contain some real super interesting information relative to the LPARS configuration, the utilizations of the LPARS, pooling of the processes of the LPAR, capacity being consumed by each of the pools, the guaranteed share, and things such as that. So with these measurements, we can answer a lot of questions. Over time, did the configuration change? Because that's how pooling changes. What was the pooling of the logical processors? Did it change during my period of time of interest? What was the parking and unparking every 2 seconds? What was the utilization of the processors? What was the decision points for parking and unparking a processor? And that's the kind of things that we get out of this particular record. So for example here, we're looking at the physical machine's utilization, right? And we see here that the machine utilization is at about 70% for this period of time, which is, I don't know what time it is, between 9 and noon, for example. And we see that it's a moderate utilization. This is from the type 70 record, every 15 minutes. Here, I guess I'm looking at the same thing, machine utilization. I guess I zeroed in. All I'm doing here is I zeroed in on the utilization. What I want to look at here, though, is we get to see the utilization every 2 seconds. So this is the same information we got out of the 98 records when looking at KEC utilization. So here we're looking at the KEC utilization every 10 seconds. Every 2 seconds. And here it's for just the 9 o'clock. In this particular case, it's from 9 o'clock until about 9:16, 9:17. So this is only 15 minutes worth of data. And I guess that's what we were doing here. Looking at this one period of time right here, we see that we have some white space, but a user complains and says, hey, look, something happened. And we see now for that same exact 15-minute period of time that the utilization of the KEC was pegged at 100%. So it might have been 80% on average over 15 minutes, but for a certain period of time, this guy was pegged at 100%. And this is the kind of stuff we want to look at to understand from a debugging point of view what was happening to performance of our systems. In our SMF type 70 records, we can get parking and unparking every 15 minutes. So what we're looking at here is a case where every 15 minutes, again, this is a standard SMF record, we have two processors that are regularly unparked. They could be high pool processors and unparked lows, or medium pool processors. Those are always going to be unparked. Low pool processors get parked and unparked, and I must have one low pool processor that looks like it's parked most of the time and occasionally gets unparked. You can kind of see here even little bits of unparked. But we get these measurements every 15-minute averages. What we can do for the same period of time I have highlighted here, we can get what the parking and unparking was like every 2 seconds. So now by looking at it every 2 seconds, I now know that I had one high pool we had no high pool processors. We had one medium pool processor that was unparked all the time, because mediums are always unparked. We had one low pool processor that was regularly always unparked. So that's what gave me the two CPUs on the previous slide. So now I know which processors I had unparked. And then what we have here at the top is the parking and unparking every 2 seconds. So here we see sort of this big block here, parking and unparking. Here we get to see the more granular view of how it parks and unparks every 2 seconds. And that's because when we look at it from a CPU utilization point of view, what the 99 subtype 12s also give us is the utilization of the MVS system. So in the previous slide, this was the KEC utilization. This here is the LPARS utilization every 2 seconds. And we get that for that's what the blue is. What the orange and green are the threshold values that the WLM is using in this particular case of when to park and unpark a processor. So the green and yellow on this chart are dynamically adjusted. Right now they haven't changed at all, but if you do capping, or there's something going on where you change the number of processors, the weights or something like that, you're going to see these values change as well. But basically what's happening here is WLM is saying regularly monitoring the utilization of the LPAR, and says if it's above the green line, consider unparking a processor. Obviously you're getting busy, unpark a processor. If it's below the orange line, then consider parking a processor. And if it's between the two lines, then don't do anything. So this helps us understand the threshold values, and you'll actually see these change based on what's happening in the system and the configuration of the system. So that's why parking and unparking occur. Another record of interest is the 99 subtype 1 record, which I mentioned contains some system-wide information. Now, to kind of go into 99 subtype 1s and 2s, actually, real quick overview or refresher is for the WLM algorithms to run, there's really two sets of algorithms that WLM has. There's what we call policy adjustment algorithms, which happens every 10 seconds. And the purpose of policy adjustment algorithms is to, the way WLM helps real workloads meet their goal values. When a goal is being missed, it's the policy adjustment algorithms that adjust the settings that cause the goals to be met, or WLM changes something in order to meet the goals. And that happens every 10 seconds. And then we have what's called resource adjustment, which happens every 2 seconds. And what resource adjustment algorithms are all about is to improve the efficiency of the processor resources. It could be that goals are being met, but you want to make sure your CPU is being utilized as best as possible. So it's the resource adjustment algorithms that might close down initiators, or might increase MPLs and lower MPLs in order to push or take away work from the system in order to make the work run more efficiently. And those happen every 2 seconds. So what happens is WLM is going to wake up every 10 seconds, every 2 seconds, and do this loop. Now, I'm not going to go through the loop here, but the point I want to bring out is the first thing it does is it monitors the system. And so what WLM is actually doing is it's summarizing lots of data in order for it to make the decision. This first bullet here is what's being cut into the SMF 99 subtype 1 and 2's records. This is what WLM is looking at in order to make its decision. That's what the 99 subtype 1s and 2s are. Next, we're going to have this flow of control, basically the WLM algorithms and how it selects a period to help, how it selects a period to steal from, what it does, how it assesses those actions. There's a concept of, all right, I want to make a change, but is the change going to be a big enough change to make a difference? Is the change going to have a positive effect on the system? And all that needs to be understood and is actually done by Workload Manager during this looping process. But what's also nice is that the 99 subtype 1s will actually give us a trace of WLM's decision-making process. Basically, what the 99 subtype 1s do is walk us through this loop to help us understand that when WLM wakes up to try to help meet a goal, what it's actually doing and what it's actually looking at. A couple of terms real quickly, just when I give you my example, we have this concept of a receiver and a donor. A receiver is what WLM is a service class period that WLM selects in order to help meet a goal. A goal receiver is one in which WLM says, hey, you know, your goal is being missed, let me help you. And that's the goal receiver. A resource receiver is one in which WLM says, hey, look, I'm going to give you resources in order to help the one that's missing the goal value. And that's a resource receiver. And then you have secondary receivers, which I'll explain in a moment. Then you have the same thing for donors. You know, a donor is someone who's going to give up something. So WLM selects donors to say, hey, look, I want to help STC high, but in order to help STC high, I have to steal from batch low. Batch low is a donor. And there's goal donors, which are the ones whose goals are going to be hurt when they're stolen from. And there's resource donors is the one who has the resources actually stolen from them. And the reason I go through that is that you have these algorithms, and I'm not going to go into any great detail, but all of the information about these algorithms and how the decisions are being made are in the 99 records. So for example, the quick little example I want to give is, let's say we have some number of periods. The circle represents a period. The level of the circle represents a CPU dispatching priority. So this period has a higher dispatching priority than these three periods. Let's just say WLM selects this period to help. And WLM says, look, I want to either raise or lower dispatching priorities. What do I do? And the 99 subtype 1 and 2 records will help us understand the process. WLM is going to say, oh, look, this is the receiver. Let me try to put him above everybody. That way he gets more CPU. He's the receiver. This guy becomes the donor. Why is he the donor? Because right now he has no competition. As soon as the receiver goes above him, he's going to have competition for the CPU. These guys are considered secondary donors because not that they're donating CPU directly, but when the receiver goes above them, they no longer have equal competition to the receiver. The receiver is going to be above them. That's one action. Another action could be I can move the donors down. That'll help the receiver by getting these guys away so they're not competition for the receiver. Maybe I want to move this guy below everybody, and these all become receivers because now they don't have the competition of this guy. Or maybe I want to move the receiver to one level up to make them equal. Or maybe I want to move everybody down to the same priority. And the reason I mention that is that that's all kind of decisions WLM is making before it actually, no, not making, considering before WLM actually changes the dispatching priority. So whenever you see something like this when looking at dispatching priorities where, oh, look, WLM raised this guy's dispatching priority and lowered this guy's dispatching priority, and you want to know, why did he do that? You know, in this particular example, it might not be that interesting, but let's say the one he lowered was DB2 and the one he raised was STC low. You're going to want to know why that happened. So by looking at the 99 subtype 1s, and I'm not going to go through all this, but by looking at the 99 subtype 1s, we get this trace information, which has WLM saying, oh, look, let me pick a receiver. Oh, the receiver I'm going to pick is this guy. You know, don't worry about the unbunching, but look, let me consider a bunch of actions with CPU dispatching priority. Who am I going to steal from? And here I'm going to move the donor down. I'm going to move, you know, some other thing up. I'm going to have a secondary donor. Let me assess that. And eventually I'm going to raise or increase the dispatching priority, whatever the decision is. The point is, this is the thought process that WLM is actually making to consider raise one guy, lower the other guy. If you compare this table, this trace here to the previous slide, you'll see why WLM raised this guy and lowered this guy. Same thing here. I raised these guys. I didn't touch these other guys, but I raised somebody above somebody else. Again, you can look at these traces and figure out why he did that. Who he selected as the receiver, why. Who he selected as the donor, why. And especially when you see a big drop in utilization, when you see a big drop in dispatching priority like this, usually you want to know why, and that's going to help us understand, you know, the traces. In the 99 subtype 2 records, we have lots of information about usage of the resources and the controls of the controls for every period. What's in there is also some measurements you may not be familiar with. So one is a countdown clock. And what a countdown clock is a way WLM defers looking at a period. So in other words, WLM may look at a period to help, and it can't help that period. Okay, he's not necessarily going to look at it the next 10 seconds. He doesn't want to look at it every 10 seconds to say, why, let me try to help, let me try to help, let me try to help. Or maybe he helps a period, but he doesn't want to look at it again for like 30 seconds because his attitude is, let the change absorb, let something happen before the guy actually starts, before I look at the guy again to help. And that's done via countdown clocks. And what this is showing us here is certain countdown clocks with WLM. It doesn't matter about the interpretation, but it gives us insight into why WLM may not be helping a period because he helped him or he decided not to help him. And he wants to just put him on the sideline for a short period of time. That's what the countdown clocks are all about. Here we look at using states. So if you're looking at using and delay samples on a regular basis in the SMF type 72 record, this is the using every 10 seconds. So if you want to understand who's using, the using CPU delay samples or the delay samples, you can look at them every 10 seconds. This is the using samples every 10 seconds. History, this is interesting for me because when you look at the 99 records, WLM doesn't just look at the last 10 seconds worth of data. It looks at the last 30 seconds, last 1 minute, last 60 minutes, so 60 seconds, 5 minutes, last 15 minutes, previous 15 minutes to give me a half an hour. And this is going to help us understand how far back in history is WLM looking at in order to make a decision. Is he making a decision based on what happened in the last 10 seconds, or is he making a decision what happened over the last 15 minutes? We're almost running out of time, so let me just go through this real quickly. One, in the 99 subtype 3s, this is our plot information. I'm not going to go into that, but just know that WLM is plotting out a bunch of information in memory, and it uses these plots. If you put them on a piece of paper, they'll look exactly like this, but it uses this plot to make projections. So here we have a summary of the presentation. There's a lot more in the 99 and 98 records. There's a lot of great information there, and hopefully what I did during this hour is kind of give you an insights into what is in these records and some possible usage of these records. I'm always interested to understand if somebody's using the records out there, if anybody wants to pipe in. My recommendation is collect the records. I don't think I would develop a real-time monitor for them, but if you're collecting the records and if you've never looked at them before, I really encourage you to send me an email. I'll tell you how to send us the 99 and 98 records. We'll process those records for you. We'll produce lots and lots and lots of charts. And then we'll have a phone call with you to kind of walk through the charts to tell you what we're seeing in your 99 records. And then you can make a decision whether or not you want to continue or cutting them, or if you want to continue, making your, doing your own development of your own reports for these records. So that's kind of what I had, Martin. Anybody have any questions? You can put them in the chat, or if anybody wants to pipe up here. I don't see anything here. Anything, Martin?
For once, I've got no questions. and you're right.
Do you use the 99 records?
I used 9914 for the topology stuff, right? Mostly to look at multi-draw LPARs and to show the home addresses being nicely corralled or not as the case. But that's it. I don't use 28s yet, and I don't use the other 99s. Subtype 6, I think we map in our process, but I haven't really got an experience in using them.
Yeah, they're really useful. I mean, the 99 records, the subtype 14s that Martin's referring to, I didn't go through an example here, but it gives us information about the topology of the LPAR's processors to the physical machine. And if I remember correctly, Martin, there's an actual tool that IBM provides free to actually do a graphical representation of that assignment.
Yes, there is. Yes, there is. Well, I'm not sure if it's still around. It may well be. Me being me, I look at them a slightly different way because I like to see whether the topology changes, and so I have a way of encoding which core and draw and so on a home address is in as a number. Then I can graph them through time. But so I do things a little differently from what that tool does. But it's even what the tool does is good because it's depicting where the home addresses are for the logical engines. That does require a bit of a sanity check because a home address, as you all know, isn't where things necessarily run unless we're talking about vertical highs. So yeah, you can see why
I would love to see your reports. I'd love to see how you represent. We also represented a certain way. Scott did some clever reports. Yeah, okay, we'll huddle. But I think we're at the bottom of the hour, Martin, so I know I don't want to keep anybody on, but always feel free to ask a question. Yes, go on. All right, I guess no questions.
No, there are some attaboys, and I'd like to add mine, Peter.
Oh, thank you, Martin. I always appreciate that from you and everybody else. So thank you so much.
Okay, there's a keynote in half an hour, I think. But that's it for this stream today. We start again tomorrow at 9 o'clock.
Okay, and if you can fill out your session evaluations, we'd certainly appreciate it.
Yep.
And thank you again, Martin, for the invitation and for hosting.
Okay, folks, I think this is it.
Okay, bye-bye, everybody.